Hello, in this video I'll be talking about electronegativity and bond dipoles. So what is electronegativity? Well, simply put, electronegativity is how we measure an atom's ability to attract electrons. So the more electronegative an element is, the more likely it is to attract electrons towards itself. And this is really important when we think about bonding, because we'll have certain bonds where we have atoms that are drawing electrons towards themselves. And we see this especially with covalent bonds where we have shared electron clouds. So remember that with covalent bonds, you have multiple elements sharing the same electron cloud because they're sharing electrons. So it gets really interesting when you have highly electronegative atoms that are drawing electrons in the bond towards themselves. So overall, electronegativity is a general pattern, and what you're going to see is that there's certain elements that are highly electronegative compared to others. And that's what I've written out here at the top of this. So this group of elements up here, fluorine, oxygen, nitrogen, chlorine, bromine, iodine, and sulfur, are the most electronegative elements that we have. And they're going in descending order. So fluorine is generally considered the most electronegative element. More generally speaking, in terms of the periodic table for all the elements, electronegativity is going to increase as you go to the right, and it's going to increase as you go up. So it follows the same general pattern as ionization energy and electron affinity. And actually, electronegativity and electron affinity are somewhat related. So they're kind of similar. They are different, but they're somewhat similar. But they follow the same patterns. Increase to the right and increase as you go up. So generally speaking, when these are in bonds, that's where we kind of see the magic happen with this attraction of the electrons. So let's look at that now. So what I have here that I've drawn is a hydrogen and fluorine bond. Now if this is the only compound we're talking about, we can call this hydrogen fluoride, or you can also think of it as hydrofluoric acid. But more generally, we'll just call this HF. And this is representing a shared bond between this hydrogen and this fluorine. So you can probably easily tell which one of these is the more electronegative atom, right? Because we have our acronym up here, Funkelbryce. So we know that hydrogen isn't in this group, so hydrogen isn't very electronegative, but fluorine is, and fluorine is extremely electronegative. So there's like a disparity between these two atoms. On one hand, for the fluorine, you have a highly electronegative atom, and for the hydrogen, you have a far less electronegative atom. So there's a huge difference in electronegativity here. And what that's going to mean is that this molecule is going to have a partial negative side and a partial positive side. And that's because the electrons are sort of going to pile up toward fluorine. That's because fluorine is drawing the electrons of this molecule towards itself because it's highly electronegative. So it's going to look something kind of like this. Right? So if you could look at this bond from the outside, and you could see like the outside of the electron cloud, you would see this huge bulge around fluorine, because fluorine is drawing all the electrons towards itself, kind of leaving hydrogen in the dust a little bit. So hydrogen isn't getting in on this electron action, but fluorine is. And what that's going to create is a partial positive and a partial negative area of this molecule. So right here, and you denote that with the symbol delta, which is kind of like an O with a curl at the top, or at least that's how I draw delta. Lowercase delta. So under the fluorine, you're going to have a negative, a partial negative, and that's because that's where the electronegativity is. Whereas under hydrogen, you're going to have that partial positive charge. And that's because hydrogen is going to have that less electronegative nature to it. So the electrons are not really going around hydrogen, but the electrons are piling up around fluorine. And that's why it's going to generate this disparity between the charges, and ultimately this is what creates your bond dipole. So a bond dipole is just how we represent the disparity of charge between two atoms within a molecule. And we use an arrow to denote that. So for this molecule here, to draw the bond dipole, we'll draw the arrow with the pointy end going towards the more electronegative atom. In this case, that would be fluorine. And we'll just put a little mark like that to make a plus sign underneath the less electronegative atom, which in this case is hydrogen. So this arrow is your bond dipole, showing that fluorine is the more electronegative atom, hydrogen is the less electronegative atom. So we have that disparity between the charges. And you're kind of showing it here too with this electron cloud bulge around fluorine. So here's another quick example. So we have carbon dioxide, and I've drawn the Lewis structure for carbon dioxide here. So we know oxygen is in the Funkelbrice, and oxygen is a highly electronegative atom. Carbon, on the other hand, is something that you'll often hear referred to as electropositive. So carbon, we definitely don't really think of carbon as being really electronegative at all. And that's because it's compared to the highly electronegative atoms, it's not really all that electronegative. So carbon is usually a great example of bond dipoles, because when it's bonded to other more highly electronegative atoms, it forms those dipoles. So how would we draw the bond dipoles for this molecule here? Well, we know there's a disparity between carbon and oxygen, oxygen being much more electronegative and carbon being far less electronegative. So what you'll do is you'll just look at both of these bonds. Both of them form dipoles. You'll have a dipole going this way, like that, and you'll have a dipole going this way. So two separate bond dipoles going in opposite directions. And this is something you'll see from time to time when you have elements with sort of bonds going in opposite directions where there's a high difference of electronegativity. Because if we were to draw the cloud around this, we would get something like that, sort of like a peanut shape, where the two oxygens are drawing the electrons and the carbon isn't really getting in on that electron action. So there you have the two opposing bond dipoles going towards the more electronegative atoms, which in this case are the oxygens. Okay, let's look at one more example with the whole bond dipole thing. So here I have the ammonia molecule, NH3. And N we know is part of Funkelbrice, so N is highly electronegative, and we talked earlier about how hydrogen isn't very electronegative. So here we have a huge electronegativity difference between this one nitrogen and each of these hydrogens. So go ahead, pause the video, and see if you can draw in the bond dipoles for each of these hydrogens in comparison to the nitrogen. So hopefully it looks something like this. So before we saw carbon dioxide with those two different bond dipoles that were going in opposite directions. Well, in this case, all the bond dipoles point towards nitrogen, because nitrogen is our highly electronegative atom. And in this case, they all kind of agree with each other because they're all going in the same direction. Because if you were to look at the electron cloud of this molecule, you would kind of get, something like that, where the bulge is around the nitrogen because the nitrogen is pulling the electrons towards it. So in this case, we would have agreement with these molecules, with these atoms of hydrogen, because they're all pointing in the same general direction. So later on, you'll kind of discover that this is called a molecular dipole, where all of the bond dipoles point in the same general direction, up towards this nitrogen at the top. So that's a general overview of bond dipoles and electronegativity, just to kind of wrap it up. Electronegativity is essentially just an atom's ability to attract electrons, and the more electronegative, the higher the ability to attract those electrons. Bond dipoles emerge where we have a bond with a high difference of electronegativity, where you have one atom that's not very electronegative and another atom highly electronegative, and the dipole is going to point towards the more electronegative atom.